Okay, so we're going to do another case study here, and in this one we're going to be taking a look at a proton. And this proton, we are given an electric field model for what the electric field looks like inside of the proton. So take a minute, try this on your own, pause the video, think about how you might approach this problem, and then we're going to get started on it together. Okay, so hopefully you felt like you had some success with this, and there's a couple things that I want to point out. First of all, that this will be an ideal Gaussian distribution. And the reason for that is everywhere outside it's going to appear as a point charge, which is not really a surprise. But on the inside of the sphere, the electric field is going to be uniform for any particular radius. And so that makes it ideal because it's a spherical distribution. We can choose another sphere as our Gaussian surface, and so it's going to be much easier to solve this problem. So it's an ideal Gaussian distribution, and outside the sphere it appears as a point charge. Now it might be easier to write this so that it looks normal. KQ R over R cubed. And now we go ahead and set up our problem. So the potential inside is what we're looking for. So the potential inside. Now that's going to be equal to minus the integral from infinity. Remember, this is always asking about absolute potential if you don't see potential difference, right? To R inside. So what is R inside? Well, R inside is going to be just from here to our Gaussian surface. So it's going to be this. All right, and that this R inner can go anywhere from 0 out to capital R. So this goes from infinity to R inside of e dot dr. Now, the thing to remember is that this is not a single function. And that's because when you're outside, it appears as a point charge. But once you reach the surface at R, we now have this new field model. And so that means we're going to have to break this function up so that it's two functions. So the potential inside is going to be equal to the potential outside plus the potential inside. Okay, so as you bring a positive test charge from infinity, the electric potential energy of that charge increases and increases and increases till you reach the surface. If this were a conducting sphere, then once we get on the inside, the electric field becomes 0, and the potential would remain the same at that point. And if you recall that graph of potential versus R, it was horizontal and then it dropped off as 1 over R as we would expect. Well, in this case, the electric field is still doing something. It's diminishing to 0 so that when R is equal to 0, there is no electric field. And that's because there's no charge at that point at the exact center. But just because the field is decreasing doesn't mean the potential is decreasing. It just means the rate at which the potential increases is decreasing. So you might want to stop and think about that for a minute, what I just said. The rate at which the potential is increasing is now decreasing when we get inside of the proton. Okay. So if we rewrite this in other terms, we get V inside is going to be equal to the integral from infinity to the outside of the proton r times kq over r squared dr. And remember, that's because the electric field outside the sphere looks like an electric field of a point charge. And that's a negative. And then we have minus the integral from r to r inside. And the field model we have there is kq little r over capital R cubed dr. And this capital R, remember, is a constant. Okay, so let's continue on, because now we just have to finish working through the details of the integration. So the potential inside is equal to kq over r evaluated from infinity to capital R minus 1/2 kq r squared, little r squared, over r cubed, and that will be evaluated from the outside surface r to r inner when we're on the inside. And so none of this should be a surprise, so the potential on the inside is going to be equal to, when we evaluate this, we're going to end up with kq over capital R minus 0. So this just becomes kq over capital R, as though it's a point charge. That's expected. Minus kq r inner squared over 2r cubed plus kq capital R squared over 2r cubed, capital R cubed. And we can cancel out some of these r's here, so those cancel with those. Okay, so we're going to get v on the inside is going to be equal to kq over capital R, and we're going to just move this term over here so that we just get the two pluses in a row. That's going to give us a kq over 2 capital R minus kq r inner squared divided by 2 capital R cubed. And at this point, you're basically done. This is finished. If you wanted to simplify it further, you could simplify it into kq over 2 capital R times 2 plus 1 minus r inner squared over capital R squared. And of course, this 2 plus 1 becomes a 3 minus all of that stuff.